Hi everyone, today we're going to try to understand the impact of social media on mental health through predictive modeling. In the early 2000s, social media changed the way we connect and communicate, sparking a revolution that continues to shape our world today. Early platforms like Friendster, MySpace, and LinkedIn laid the foundation, but the game truly changed with the launch of Facebook in 2004. This was quickly followed by YouTube in 2005 and Twitter in 2006. These platforms didn't just connect people, they started influencing how they think, behave, and interact. Fast forward to today, and social media is central to our relationships and daily lives, particularly among younger users. It's where families stay in touch, friendships flourish, and social interactions thrive. The connection between social media and mental health is undeniable. Researchers are exploring this relationship to create interventions that use social media's potential to its fullest. Tools like telehealth platforms with chat functions, trending educational content, and interactive features for tracking and journaling are already being developed. Advances in artificial intelligence are also helping to detect early warning signs of mental illness and identify vulnerabilities in users. But for these efforts to truly succeed, we need robust predictive models. These models must account for population diversity, usage trends, and behavioral impacts. They are essential to refining and scaling interventions that can make mental health care more accessible and effective. Mental health stakeholders, researchers, doctors, academics, and patients are united in their focus on creating accessible and equitable care. However, there are challenges that continue to persist. Early detection is difficult, treatment options are limited by stigma and cultural barriers, and efforts to increase awareness, while helpful, have not been enough. Rising suicide rates, earlier onset of mental illness, and increasing severity across age groups highlight the urgency of the problem. Research points to several contributors, um, or points to several contributing factors, such as humanitarian crises, forced displacements, traumatic events, and environmental disasters. Certain professions like first responders, military personnel, and police also face significantly higher risks due to the nature of their work. According to the World Health Organization, 1 in 8 people globally live with a mental health condition, yet 71% of those experiencing psychosis don't receive care, and only 2% of health budgets are allocated to mental health services. It is for these reasons that we needed to explore ways uh, to reduce the impact of social media on the well-being of humans. The dataset used for this project was originally designed as part of a data science and machine learning initiative. Its purpose was to explore the relationship between the time spent on social media and its impact on mental health. Data collection involved conducting a survey, organizing the responses, and applying machine learning techniques to build a predictive model. The goal was to identify individuals who might benefit from professional mental health support based on their survey answers. This survey was conducted on a university campus, and the dataset was later shared publicly on Kaggle.com to encourage broader exploration. However, the dataset comes with significant limitations that are important to address. First, the sample primarily represents university-affiliated communities, limiting its relevance to broader populations. For example, only 4 occupational categories are included: school students, university students, salaried workers, and retirees, leaving out groups like hourly wage earners and unemployed individuals. Additionally, the dataset lacks critical demographic details such as religious or spiritual beliefs and ethnicity. This omission reduces its ability to capture a holistic view of diverse experiences. The age distribution is another limitation. Participants are heavily skewed towards individuals in their 20s with minimal representation of other age groups within the range of 13 to 91 years old. These demographic constraints highlight the need for caution when interpreting findings. While the model may perform well within the dataset scope, applying its insights to broader or demographically different populations could result in inaccuracy. As we work to build a predictive model, the 7-step business analytics process will be used. The business analytics process is structured into 7 key steps each critical to delivering actionable insights. We start with step one, business problem understanding, where we define the objective and identify how analytics can solve or how analytics can address the problem or create value. Next is step two, data understanding and collection, where we gather relevant data, assess its quality, and identify potential biases or gaps that could impact the analysis. In step three, data preparation and feature selection, we clean, organize, and refine the data, selecting key features while removing irrelevant or skewed variables to ensure the data is ready for modeling. In step four, modeling deployment, which involves applying algorithms like regression decision tree or neural networks to create predictive or descriptive models. The data is split into training and testing sets to validate performance. In step five, model evaluation and interpretation, we assess the model's accuracy and other metrics like precision and recall to ensure it meets the defined business objectives. And then in step six, model results communication, we present the findings to stakeholders in a clear and actionable way, using visualizations and tailored explanations for both technical and non-technical audiences. And then finally, step seven, model deployment, it's the point in the business analysis steps where we integrate the model into business processes, enabling automation and monitoring to maintain performance and relevance over time. For this case study, I used RapidMiner's AutoModel feature to evaluate how effectively the data could support the creation of a predictive model. To start, we made some adjustments to the dataset. Many demographic-related nominal features were excluded due to uneven distribution across categories, which could skew the results. Additionally, variables like rates of mental disorders by gender and age were deemed more appropriate for analysis outside of the predictive model. When the refined data set was uploaded to AutoModel, we set the frequency variable as the target. This allowed us to study how mental health reporting influences it. For the independent variables, we included the following factors: concentration difficulty, distraction, restlessness, variance in activity interest, anxiety, depression, hours spent on social media, self-comparison, sleeplessness, number of platforms used, validation-seeking behavior, and post-sentiment. These variables were selected for their relevance to the relationship between mental health and social media usage. To kick off our understanding of the results produced by RapidMiner's auto modeling, we will start off by looking at the weights. At the top of the list, we can see that concentration difficulty and distraction are the most influential factors in our model, making them key drivers for the predictions. Following closely behind are restlessness, activity, and interest variance, and anxiety, all of which contribute significantly to the model's accuracy. On the other hand, features like validation seeking and post-sentiment have minimal impact. This suggests that these variables contribute very little to the model's overall predictions and may not be might not be as critical to focus on in future iterations. Understanding these weights allows us to prioritize the most impactful features, helping refine our analysis and improve the model's performance moving forward. After running the auto model, 5 models were generated: a random forest model, logistic regression, naive Bayes, deep learning, and decision tree. Among these, random forest proved to be the most accurate, achieving an accuracy score of 82.4%. Logistic regression and naive Bayes closely followed, with accuracies of 81.7% and 81.6% respectively. Decision tree and deep learning had slightly lower accuracies at 79.6% and 78.1%. In terms of efficiency, logistic regression emerged as the fastest and most efficient model, with very short training and scoring times. On the other hand, random forest, while delivering the best accuracy, was the slowest to run. Overall, if you prioritize speed and efficiency, logistic regression strikes an excellent balance between accuracy and runtime. However, if accuracy is your primary concern, random forest is the clear choice, albeit with longer processing times. For this first model, we'll be taking a closer look at the naive Bayes. A naive Bayes is a simple and fast machine learning algorithm used for classification tasks. It is based on Bayes' theorem, which calculates the probability of a class based on prior knowledge and assumes that all features are independent of each other. Despite its simplicity, naive Bayes works well for many applications like spam filtering, sentiment analysis, and text classification. In, re- in reviewing the naive Bayes model results, the model achieved an accuracy score of 81.6% with a classification error of 18.4%, indicating a reasonably good overall fit. The area under the curve had a score of 86.7%, which demonstrates strong discriminatory power between the two classes. Precision and recall are balanced at approximately 83%, leading to an F measure of 82.9%. This indicates that the model effectively identifies positive cases while keeping false positives to a minimum. Sensitivity, or the true positive rate, is 82.9%, while specificity, the true negative rate, is slightly lower at 79.4%. This suggests the model is more adept to correctly identifying positive cases than negative ones. The confusion matrix shows that most instances are classified correctly, but there are 12 false negatives and 13 false positives. These misclassifications highlight areas where the model could improve, particularly for the minority class. Now we will take a look at the logistic regression model. Logistic regression is a crucial tool for predictive modeling and analytics, particularly when the goal is to model the relationship between a set of independent variables and a binary outcome. Its simplicity, efficiency, and interpretability makes it a go-to method for classification tasks. The results from the logistic regression show that the model delivers consistent performance with an accuracy score of 81.7%, classification error of 18.3%, and an area under the curve of 86.6%, which demonstrates strong discriminatory power between classes. Um, Precision and recall are both high at 85% and 84.9% respectively, yielding an F measure of 84.3%. This indicates the model strikes an effective balance between identifying positive cases and minimizing false positives. Sensitivity, or the true positive rate, is 84.9%, while the specificity, the true negative rate, is slightly lower at 76.9%. This shows that the model is better at identifying positive cases than negative ones. From the confusion matrix, we observe 12 positive and 13 false negatives. While the model performs well overall, these errors highlight areas of improvement, particularly in correctly classifying the minority classes, which is individuals without social media. For our next model, we'll be looking at the deep learning model. Deep learning models are essential in modern analytics due to their ability to handle complex, high-dimensional data and uncover intricate patterns that traditional models may miss. They are particularly powerful for tasks requiring advanced feature extraction and nonlinear relationships. The, uh, the deep learning model achieved an accuracy of 78.1% with a classification error of 21.9%. The model also achieved an AUC of 87.9%, indicating a strong ability to distinguish between classes. Precision is 76.5% and recall is higher at 85.7%, resulting in an F measure of 79.7%. The model performs better at identifying positive cases with a sensitivity of 85.7% compared to a specificity of 71.7% for negative cases. The confusion matrix reveals 11 false positives and 19 false negatives. While the model performs well overall, these errors suggest potential improvement opportunities, especially in correctly classifying the minority class individuals without social media. For the fourth model, we'll take a look at the decision tree. The decision tree models are widely valued for their simplicity and interpretability, making them an excellent choice for understanding complex decision-making processes. They provide clear visualizations for classification rules and are effective in handling both categorical and numerical data. The decision tree model results show that we achieved an accuracy score of 79.2%, reflecting moderate performance. in distinguishing between classes. Precision is notably high at 87.9%, although recall is lower at 76.6%, resulting in an F measure of 81.5%, which indicates reasonable balance between precision and recall. Sensitivity, or the true positive rate, aligns with recall at 76.6%, while specificity, the true negative rate, is slightly better at 81.7%. This suggests the model is more adept at identifying negative cases than positive ones. From the confusion matrix, we see 9 false positives and 19 false negatives. While the model performs well overall, the higher number of false negatives highlights room for improvement in identifying positive cases. Lastly, we'll take a look at the random forest model. Random forest models are a cornerstone for machine learning, prized for their robustness and ability to handle complex data sets with high dimensionality. By combining multiple decision trees, random forest enhances predictive accuracy and reduces the risk of overfitting, making it a reliable choice for classification tasks. The random forest model demonstrates strong performance with an accuracy of 82.4% and an impressive AUC of 90.3%, indicating excellent discriminatory power between classes. Precision is high at 85.2%, and recall is also strong at 84.9%, resulting in an F measure of 84.4%, which also reflects a well-balanced performance. The model is slightly better at identifying positives with a sensitivity of 84.9% compared to a specificity of 81.2% for negatives. The confusion matrix highlights 11 false positives and 13 false negatives, suggesting the model is overall better at identifying negative cases. Random forest's ability to achieve higher accuracy while maintaining a balanced performance makes it a powerful tool for predictive analytics. To better understand how the different models compare to one another, an ROC curve was used. So an ROC curve shows how well a classification model distinguishes between classes by plotting the true positive rate, or the sensitivity, against the false positive rate. It helps evaluate a model's performance and compare different models with curves closer to the top left corner indicating better performance. As shown in the ROC curve from this project, the performance of the 5 models, naive Bayes, logistic regression, decision tree, deep learning, and random forest, they are compared. The ROC curve highlights the trade-off between the true positive rate sensitivity and the false positive rate for each model. The closer a model's curve is to the top left corner, the better its performance. Logistic regression, decision tree, deep learning, and random forest demonstrate strong discriminatory power, with curves that approach the top left corner. In contrast, naive Bayes shows weaker performance with its curve closer to the diagonal line, which represents random guessing. This analysis identifies logistic regression and random forest as the top performing models, combining high accuracy with excellent discriminatory ability. After analyzing the different models produced and going back and reviewing the data set, I encountered challenges in creating a reliable predictive model for the relationships being studied for this case. Specifically, I was unable to predict how social media usage influences individual subjective ratings of mental health symptoms or disorders. Similarly, I couldn't develop a model that accurately predicts how mental health symptom ratings might influence social media usage. The models we tested consistently failed to achieve classification performance or accuracy above random chance. While some correlations in the data initially seemed promising, they did not meet the threshold needed to make them practically useful for modeling purposes. That said, this does not mean the problem is unsolvable. It is possible that a more comprehensive and diverse data set could lead to better results. For instance, incorporating broader comparison groups with more varied attributes might enhance both the accuracy and just overall reliability of the model. So let's talk about why having proportionate classes or balanced data sets is so important when developing a predictive model, especially in classification tasks. First, Balanced classes lead to better model performance. When one class dominates when one class dominates the other, the model can become biased towards predicting the majority class, ignoring the minority class altogether. This results in poor generalization and a model that doesn't perform well in real-world scenarios. For example, in fraud detection or medical diagnosis, you don't want your model to overlook the rare but critical cases just because they're less frequent. Next, evaluation metrics are far more reliable with balanced data. In imbalanced datasets, metrics like accuracy can be misleading. Imagine a dataset where you have a 95% or 95% of the data belongs to one class. A model that predicts the majority class every time would still score 95% accuracy, but it wouldn't actually solve the problem. When classes are balanced, metrics like precision, recall, F1 score, and AUC, ROC give you a clearer picture of how well your model performs. Balanced data sets also allow for a better learning by the model. With underrepresented classes, the model lacks enough examples to learn their unique characteristics, which leads to a poor performance on those cases. By ensuring a balanced distribution, the model captures patterns for all classes more effectively. Finally, let's not forget the real-world impact. In many applications like predicting heart disease or identifying defective products, the cost of missing a minority class prediction is much higher than misclassifying a majority class case. Balancing your data helps the model avoid these costly mistakes. So now what can you do if your data set is imbalanced? Here are some techniques that I looked into and wanted to provide. You can use oversampling methods like smoke to increase the size of the minority class or undersampling to reduce the majority class. Adjust the class weights in your loss function to make errors on the minority class more costly. uh, Leverage synthetic data generation to balance the data set, or you could also focus on custom metrics like F1 score that consider class imbalance. In summary, whether you achieve it through balancing your data set or compensating with techniques addressing class proportion, it is critical for building fair, accurate, and practical predictive models. Based on the current data, we are unable to make any definitive predictions that could effectively support a business model. This case study underscores the critical role of high quality, well-rounded data in producing meaningful and actionable analysis. Let me elaborate just a little more though. The dataset primarily consists of university students ages 20 to 29, all of whom report experiencing some level of mental health symptoms or perceived mood disorders. Unfortunately, the absence of the comparison group, individuals without reported symptoms, makes it difficult to establish a clear relationship between mental health and social media. Similarly, the lack of a sufficient comparison group of non-social media users further restricts the dataset's potential for broader insights. With that being said, our analysis did reveal a notable trend. Nearly all social media users in this dataset reported experiencing behavioral symptoms or mental health distress. While this is not enough to build a predictive model, it does provide a valuable opportunity for further exploration and actionable insights. And as this presentation is coming to an end, I wanted to address the challenges of understanding the impact of social media on mental health. Um, a collaborative effort is essential for this to be successful. By partnering with platforms such as Meta, X, or Snap, alongside health experts, um, we can develop an effective screening tool. This tool would be used to improve our ability to measure the effects of social media on mental health and enable better data collection from diverse comparison groups. With its enhanced data set, we recommend using predictive models like decision tree or random forest algorithms. These methods excel at handling complex relationships within data and can deliver accurate predictions. Once deployed, these models would need to be rigorously evaluated for accuracy and reliability, including cross-validation to ensure that they perform well across different scenarios. Once optimized, these models could then be integrated into devices or platforms, providing mental health stakeholders with actionable insights. These insights could guide efforts in raising awareness improving treatments, and designing targeted interventions effectively. Thank you for your time listening to this presentation.